So our next speaker is Shenlong Wang from the University of Illinois Department of Computer Science. He's an assistant professor specializing in computer vision and robotics, and his recent work is focusing on simulating realistic content to train and validate autonomous systems. He finished his PhD at Toronto, and he worked at Uber. And he has several awards, including Amazon Research Award, CVPR Best Paper Award candidate, IRAS Best Application Paper finalist, and NeurIPS Top Reviewer. So he has filed over 25 patents, and he has received fellowships from various places, Facebook, Adobe, Royal Bank of Canada, and we're glad to have him here. Thank you.
All right. Great. Can everyone hear me? All right, great. Thank you for the introduction. And I appreciate everyone being here, and especially I thank the organizers for setting up this workshop on generative AI. I think it's a very timely workshop given the significant advances in this field during the past few years. As some of you might know, I work on computer vision, and many of my colleagues, in the past 2 days already, demonstrate how much, great advances that CV as a community has achieved in the past few years. So here I just want to highlight two important directions that CV has advanced significantly during the past 2 or 3 years thanks to generative AI technologies. So one is from a modeling and understanding perspective. So now we are able to accurately construct a 3D representation given a bunch of images and videos. And that could encode both strong and accurate appearance information as well as geometry information about the scene. And on the other hand, generation, as Greg just described, it enables us to create new, non-existing visual content, such as images and videos and even 3D objects that looks realistic. And depending on how much we rely on, observations and how much we rely on, data-driven models that conduct some form of imagination, right? We can put those two types of methodology along the two ends of the axis, right? Where modeling is mainly rely on observation. They're trying to best establish a representation that depict what we have observed, while generation basically create visual content out of nowhere, right? So this is a difference. And today, my talk, instead, I want to focus on something in between. So it's another type of visual generative AI task that we could see in between that leverage both, and which I personally believe is also important and it's fun. That is recreation. We call it recreation or imagination or simulation, where essentially we want to recreate new visual experiences based on some of the observed images and videos. So let me elaborate a little bit about more and to show some of the examples. So to put it simply, the ability of recreation essentially just respond to some of the what-if questions in reality. Taking a look at this image, it's a beautiful sunny day in a German street, and we're driving on the street. There are not many people, and I want to have one question for audience. Can we envision a situation where this thing, instead of being sunny, it's being, full of smokes, or it's in a foggy day? Let's just, mentally thinking about that and trying to depict a picture about the same thing under this situation. Right? We are able to do that, right? It might not be really hard. It looks something like that, right? And what if this thing gets covered by snow? Can we imagine this could happen, right? And this might be something that we look like, the snow look like. What if the empty street now gets populated by humans? And we might be able to imagine the situation where a lot of humans that are working in the street, and there could be some busy events that happens, and so on and so forth. What if instead of taking this a photo of this thing at daytime, what if we take it at night? right? So we should be able to also reason something like that or something even more, extreme, right? For instance, I hope this street never gets flooded like this way, but, is that possible that we can create such an experience? That is rare, that might not yet happen, and it's totally counterfactual, but it looks realistic just as if it will appear, right? So I hope this can convince you that we humans, we have a recreative mind. Formally speaking, we can think about the world in our brain from a perspective that is different from our current experiences. To grasp such imagination capacities, studies in cognitive science, they argue for that we essentially need to excel at two things. So one is we must perceive the world from our sensory data properly so that we can understand our world. And secondly, based on what we have been perceived, one must be able to create all those experiences of sensations as if they actually happened in front of our eyes. So the goal of today's presentation is we want to empower computers with the ability to also imagine in such a 3D physical world, right? The two key terms are essential, reflect the desired properties. So imagine refers to the creation of non-existent scenarios over a existing world. And the second point is that it has to be grounded by the reality, by the physical world, which distinguishes it from a purely generative approach that just creates out of nothing. So in fact, all the images I show here, we saw before was automatically generated by the method that we'll discuss in today's talk. All right, but before we delve into how we achieve this, one might ask, why do humans or why do computers, right, need this type of visual recreation, right? So building computational models that recreate new experiences in our 3D world can make people to be better, communicated, through each other. For instance, through immersive computing, right? We can basically teleport our friends and relatives like 1,000 miles away, in front of eyes, just appear like, we are discussing them face to face, right? It brings distance between humans closer. And on the other hand, we might be able to better, help to predict what will happen in the long run, like simulating climate extremes, or, to help our autonomy to handle those type of, dangerous yet important, situations in a safely manner, right? And more importantly, we could potentially help, important decision makers to choose or to make informed decisions based on different alternatives and based on the evaluation of different counterfactual situations. So in general, a lot of opportunities are there, but we haven't reached the stage where we can seamlessly bridge the real and the imagined world. So before I talk about why, let's firstly start a visit what we have achieved, what are the opportunities here. So from a 3D perception side, I have advanced tremendously in the development of semantic and geometric understanding. For instance, a neural radiance field that can help us to encode rich appearance information, and our semantic fusion and other stuff could help us to identify the semantics of different objects that are there in the 3D world. So our understanding of 3D world is deep now, but most of the representations that has established by those algorithms, they are meant to just encode those facts, encode knowledges. It's very hard to take actions on top of them or make plausible editings on top of them. So another highlight of our community is just generating AI techniques like image generation and image editing. So now they are able to create or edit images and videos that look aesthetically really pleasing. Yet it's impractical for informed decision making in the real world simply because the lack of form of grounding in physics and in geometrical reality. For instance, on the right side, I show the latest, greatest video editing tools from Runway ML. Basically, they are able to realistically, stylize an image, but we can see that the it does not look like it's an image that captured in the physical world, because you can see the background of the buildings, they keep changing, and also the human face, they have been keep changing. It does not look like it's rendered, from a realistic, lighting conditions and so on. So it lacks some of the physical grounding. On the other side, computer simulation has been there for decades, right? That is the opposite situation. So it's based on physical rules. And we are able to model a lot of accurate physical interactions, for instance, particle interactions, rigid body or non-rigid interactions, and so on and so forth. But it requires specialized representation with accurate physical properties. That means we have to make this simulation happen by manually design those assets that has certain physical properties. This is terribly hard if we want to create a digital representation directly captured from just a piece of videos from the real world. So to close this gap, inspired by our advances in data-driven method and physical methods, our key insight is we want to combine the best of the two worlds. We want to leverage a data-driven method in terms of capturing and leveraging the existing visual data, but in the meantime, we want to leverage physical-based modeling so that we can make sure that our recreated experiences are grounded by physical knowledge. All right, so today's talk will discuss several efforts to address the aforementioned drawbacks and trying to illustrate this idea of combining data-driven and physical-based methods. So let's start from the first question, right? Can we model an editing like lighting physics? Can we, can we relight the scene so that we can change this video from daytime to the nighttime? Right. So I really appreciate Greg already gave a really nice tutorial on neural radiance field. So the NeRF thing is essentially a 3D scene representation that allow us to encode colors and appearances, and also to render from different views. And specifically, I want to just quickly revisit that. So the NeRF essentially just a neural network, which its input is a 5-dimensional Curie location, where it includes 3D location and viewing direction. And its output is just that point, density and color. When we do the view synthesis, when we render from this NeRF representation, we will shoot out a camera ray, and then we'll densely query a lot of points along the ray and getting their color and density, and then suppress them together and basically integrate them together through a technique that has been used in graphics that is called volume rendering. And then finally, we will get the rendered color for each pixel, which is also corresponding to that camera ray. And then we can have supervision to the neural radiance field based on our observed colors of those camera rays. And after we supervise them, what we can achieve is, given a bunch of images across different views, we are able to establish a NeRF representation, allowing us to render from different perspectives. That being said, standard neural radiance fields, they directly encode observed color. We might know, right, the observed color is just a final effect between the interaction between our external things, which is our lighting conditions, and our intrinsics, which is our materials. So NeRF does not disentangle these two. That means it makes it unable to produce alternatives. We cannot really render this screen under blue light, because we only see is this screen rendered, lit by some of the yellowish illumination, right? So to overcome this, the goal is we want to establish a representation that can encode geometry, lighting, and surface materials. And in this way, one can relight the scene using a hypothetical illumination and edit it with the hypothetical materials. So there are already existing works that are trying to achieve this goal by establish some of the reliable NeRFs. That being said, existing work either focus too much on very densely data collection and at somewhat object level. And there are a few works that can conduct in the scene level, but they often require additional conditions. For instance, the scene has been illuminated under multiple lighting conditions or with some known geometry, which are unrealistic from a single shot of videos. So our work here is trying to recover the lighting physics from a large unbounded scene using a single video. Specifically, the input is just a single monocular video under single illumination. And then we will establish a scene representation that can encode something in the middle, like the surface normal and also the visibility, which actually encodes the shadows, and also albedo, which basically encodes the intrinsic color of the material that has nothing to do with lighting conditions. All right? By establishing this type of composable scene representation, we could achieve quite a few different tasks. For instance, we can relight in a different angle, or we can relight the scene from a different lighting conditions, like a different time of the day, or we can insert a object in a realistic manner, such as the interaction between the existing shadows, the existing object, and these inserted new actors are realistic. And finally, we can also simulate some of the totally different illumination conditions. For instance, we take the scene we take the photo at the night time. All right. That being said, this is a very challenging problem. There are two key challenges. As we can see, this unbounded scene, they are very, very complicated. It's much complicated than a single object. So this implies there will be a complicated interactions, because lighting interactions between the objects. One obvious example is the Cassie shadow, right? So for the same surface, we might perceive very different color, because depend on whether those surface is under the shadow or outside the shadow, right? The other challenge is because given the fact that it's a single video, this makes a problem fundamentally ill-posed and consequently very challenging. So this is work led by our student Zhihao and many others, including David here. And we instead have two key insights trying to tackle these two challenges. The first is, given the fact that it's an underlying ill-posed problem, we want to leverage as much strong prior knowledge that we can have. One is leverage data-driven monocular cues as a prior. So we have know that single image monocular perception has been advanced a lot, and given the fact we have a lot of data, we can train surface normal prediction very well, we can train semantic segmentation very well, and we could also conduct a monocular shadow estimation and even a monocular albedo estimation, or what we call shadow removal. So these data-driven priors are nowhere close to be perfect. So they do have a lot of artifacts. They are not consistent, yet they already could give us very informative, strong regularization of priors to our problem. And the second insight is we want to establish a physical-based model to relate the observable shadows to the geometry of the area. Let me try to elaborate a little bit. Suppose we see these two dots. One dot is a blue dot, which is under the shadow. One dot is a red dot, which is basically on the wall, which is outside the shadow, right? Given those information, what can we infer? So we know that if the red dot is outside shadow, suppose we have one ray that connect between the red dot and the lighting source. We know that there is nothing there because they shouldn't be block the rays, right? That being said, if we see a blue dot under shadow, we might already infer, although we cannot directly observe any occluders, but we might already confidently infer there are something that's blocking our rays, blocking our sunlight, right? This might give us a very strong cues about how the geometry of the scene looks like. By leveraging these two perspective, we are able to establish a novel, relatable scene representations. So we start from just a 3D implicit representation, similar as NeRF. That being said, our representation, instead of directly give us a color, we encode surface normal, semantics, and our albedo color within this representation. So given an observation ray, we firstly curate those information, and in the meantime, we we are able to follow the physics of shadowing process, trying to render out a visibility map by shooting a ray between each scene point to the lighting direction, so that we are able to get a realistic visibility map as well. And then we'll just following the physics of light propagation and shading process. We are able to get realistic shading that reflects both the sun color and the sky color, and then compose them together with our materials, which give us the final render image. And then in order to optimize these 3D representations, so we have a few loss functions, which is guided by, firstly, we still need our rendering to be consistent with our observation. And then we should also ensure that our shadow rendering process follows the physics of shadow propagation. And thirdly, we want to inject those priors, monocular priors, on both the shadows and normals and semantics and albedo, as we discussed before, that we could leverage a lot of data-driven monocular perception network to conduct that. And the results given is something like that. We are able to estimate surface normal, we are able to estimate normal albedos and shadings, and we can also render colors from our observation. This is from observation views. And after we get these observation views, we could enable something different, right? Especially before I move on to that, I want to highlight that, as we can see, right, we basically totally remove all the observed shadows from the scene. And this basically weird-looking color image essentially depicts the intrinsic material or intrinsic color of the environment. That is, lighting environment. All right. So afterwards, we are able to do something like change the direction of the sun, basically to mimic a time lapse of the change of the day at the same position. And as you can see here, the shadows have been moving and in a realistic manner as the sun that's going towards that direction, right? And in another case, the sun is moving from the left to right, as we can see the shadows correspondingly moving from the right to the left. All right, so we could also simulate the night simulation, like what we have seen here. So given a sunny day, and we can simulate what if we drive at night in this thing, right? There will be highlight and there will be street light pop up. And importantly, we could showcase that by explicitly model the physics of shadow, we could see that if we want to insert an object into the scene, the interaction between the shadow field and the object is quite realistic. The shadow has a very sharp boundary, just like what we could anticipate in the real world, and when the object gradually moving into the scene. If we, without explicitly modeling the shadow, what we can get is a bunch of blurry images because of the floater issue that has been seen in the neural radiance field representations. So this is one of the key take-home message. I think it's important for us to model shadows explicitly using physical-based models, using optical physics to get a good inverse rendering process. All right, so I will pause here if you have any questions before we move on to the next step. All right, if no more questions, this basically summarize our first part of how can we manipulate or edit lighting physics. Next, we want to discuss about another question. Can we model and simulate effects that be beyond the lighting? In this work, what we will demonstrate is how can we simulate realistic climate effects based on just a single observation on the top left. And here we show 3 different climate effects, for instance, like having the flood and having smoke and snow into the scene. So let me briefly describe how it works. So essentially, given an input video sequence in the form of multiple images across different views, still under the same climate condition, and also we have a target climate effect. Say we want this thing to be snow. To get snows. So we firstly build a neural scene model, which is essentially like a neural radiance field, which encodes geometry, semantics of the scene, and allow us to render photorealistically from any viewpoint of this playground. And next, we could apply a generative AI editing approach to obtain edit images of winter scenes. If you use Stable Diffusion, we can just say, make this image to be snowy, right? And this generative AI approach does try to change the global weather effect. And as we can see, the green vegetation becomes winterish black, and the ground becomes whitish, and so on and so forth. That being said, I don't think that is enough. I will pause a little bit here, and we can zoom and watch it again. You can see what is missing, right? So although that we want to turn it into a snowy scene, but there is no snow actually appears. It just gave us some whitish color that changing everything to be whitish, trying to mimic snows, but there is missing the physical entities of the snow particles and snowballs. So that is not enough. So what our approach is, we just let it snow, and we will simulate those weather related physical entities into the 3D scene. Like literally we drop snow particles from the sky to our digital model. And when it hits the surface, we'll accumulate some of the snows here and there so that finally we'll get our final rendering of the scene. As you can see, a lot of snows have been accumulated, and our ray tracing will basically merge those physical entities and NeRF models by carefully accounting their optic physics interactions during rendering. So I will go a little bit details here, as this is one of our key approach. Basically, in order to produce a realistic physical phenomena like flood and snow, and we want to add those entities into the scene, and those added entities will impact the light transportation in the scene. For instance, like smoke is some of the semi-transparent volumes, and water is just rippled surfaces which will reflect the light back into the scene, and we need to curate those light to mimic reflection and refractions. And snow particles are just a bunch of particles that scattering light. As we can see here, if we hit the snow, it will scattering around, and we will mimic this type of physical processes, trying to make their rendering to be as realistic as possible. Due to the time constraint, I will skip a little bit. We can see that we could get this playground to be flooded with some of the dynamic water surface, and we could also make it to be covered by a lot of snow particles, and we could simulate different level of snows as well, because our simulation is purely physical based. That means we can easily control the different level of severeness of those climate effects. Right? In short, so Climate NeRF is able to manipulate the climate of the scene while being realistic, view consistent, and also highly controllable. And similar techniques can be actually easily extended. 2 weeks ago, my PhD student, Zhihao, who is the first author here, just did a short video celebrating the fall seasons. As we can see, we can treat those fallen leaves as also particles and putting them down to the ground, and using generative AI, which is data-driven approach, trying to change the style in the background to make us to feel that there is a fall season experience. All right, so this Climate NeRF stuff can generate across different arbitrary videos automatically, so long as we can just take a video of the outdoor scene, and then we can build a NeRF, and Climate NeRF can handle all the rest. And as I mentioned before, it's highly controllable. We see different level of severeness and so on and so forth. And here is one important note that I would like to stress here. This is what we have learned about building this climate simulation process. We have noticed that neural network is a neural radiance field is really good at rendering at different node views and so on and so forth. That being said, what we have learned is rendering quality is not necessarily equivalent to simulation quality. As we can see here, on the top is instance NGP is one of the latest, greatest, maybe not latest, but one of the greatest neural radiance field methods 1 year ago. And on the bottom is our NeRF models. In fact, in terms of novel view rendering, if you take a look at the left, So the NGP and our method actually gave us very similar rendering qualities if we see this half of the images. So basically, in terms of PSNR estimate, we didn't really notice any difference. That being said, when it becomes, applying our, weather simulation effect, we could see there is a huge difference. Because of the fact that this neural radiance field, they learn to render so that we give them a lot of freedom in terms of trying to mess up with its geometry, mess up with its density, and so on and so forth, making their geometry is actually not realistic, which brings a lot of trouble in physical simulations. You can see that there are a lot of artifacts in terms of when we want to insert the waters or when we want to insert the snows. In particular, in the snows, there are a lot of snow particles that accumulated on the trunk of the tree, which is not realistic at all. That being said, from just a novel view synthesis, this type of mistakes or errors in geometry modeling was not really exposed from just a PSNR. So it has to be exposed when we run simulations on top of that. And we can see in those type of counterfactual scenarios, those type of artifacts has been exaggerated. This suggests a future direction that when we want to build a 3D representation, probably we should not only just think about how we should encode existing knowledge from our observation, but we should also think about how can we use it for actions, for taking actions, for editing, and so on and so forth. All right, so now next, I want to show some of the interesting applications. For instance, we could simulate how the sea levels has been raised. Suppose the climate change situation was still there. And I will skip some of the examples, and our method can also simulate, different weather situations on urban driving scenes. That might demonstrate some more potentials for us to, train and test our driving vehicles under adverse weathers. For instance, if we just apply a standard 3D object detector, trained on standard data set, which is usually just cloudy and sunny days, we are fine. That being said, when our smoke becomes thick and thick, those type of methods started to fail. Well, this also suggests that if we are able to simulate a lot of this type of smoke stuff, it could be potentially augment our training data to make our perception algorithm to be more robust to those situations. All right, so I still have 10 minutes. Next, I would like to really discuss about, so far we have discussed about, how can we use the recreation to, edit videos and create beautiful videos or create beautiful videos from different view perspectives. That being said, is that possible that we could leverage similar techniques to build a truly interactive virtual world, to actually create a digital twin from our observations and make them to be a computational environment that we can feel free to interact and to create a lot of counterfactual scenarios, using computational method. So here we'll start from GeoSim, which is a work that we have been done 2 years ago. The goal is trying to ask whether our cars can operate on some of the safety-critical counterfactual scenarios. For instance, what if there is another car that's cutting our line and making a sharp right turn? Is that possible? Our autonomy system is able to handle that. So we actually explore this type of also recreation technique, which is essentially called insertion rendering. So specifically, we insert these new actors into the video in the way that we can test how our perception will react. This is not as simple as we thought, because just simply copy and paste has a lot of issues. So the lighting condition from this car that captured and also this target environment is very different. And also there could be some of the complicated interactions. For instance, this area has been blocking this car and so on. Also, that car needs to behave in a realistic and convincing manner into the scene. So in order to achieve that, I will skip some of the details due to the time, but overall it's also a combination of physical-based methods that trying to simulate the car's behaviors so that the car is moving realistically in this target scene. And in the meantime, we also leverage some data-driven methods trying to post-process our render video so that those actors are seamlessly blended into the target scene, just as if they actually appear here. Now, I want you to focus on this video. There are two, fake cars, two cars that actually does not exist in these scenes. Could you trying to recognize which one is not really realistic? All right, so here I want to highlight 4, right? There is a red car, blue car, yellow car, and a black car. There are actually 2 fake cars. Which 2 do you think, it's fake? Yes, Greg? Red and yellow. Any other question, any other answers? David saw that before, so. Any other answers? Could you give a different answer? Red and black. Any other answers? Yeah, I think we noticed that red is not the true one, but the answer is actually the red and black. So for red, you can see that I think the focusing effects, the auto focus effect is not really convincing, and also the shadow was not casted on the car, right? This is some of the obvious effects. For black one, it's also, I think there are some artifacts in terms of auto focusing after we compose, but because it's really far away and it's blurry, it might not be easy to see from this screen. But yeah, those are the realistic, videos that we could compose. Here is another example where we actually simulate 2 cars that are running the red light in front of our police cars, which is quite rare and quite unusual in most of the situations. And that being said, there is still significant drawback, right? We might already see this is still a video editing technique, right? So even if there is a car in front of us, if our autonomy decide to brake, then it will generate a totally new visual experience from background as well, because our pose is different. That being said, here is we haven't been able to create an interactive world that our agent can freely explore these visual scenes, can generate whatever depending on its own actions. This is still an off-policy, video, right? So to overcome that, this is one of our latest works that have been, that will be potentially archived very soon. So in this task, our input is just a single monocular video. Then our goal is we want to directly output a real-time, realistic, and interactive environment. Essentially, we want to turn a video into a game, and technically with in a fully automatic manner. Here we show 2 games. One is a car racing game. One is just a character that is running in the street, collecting coins. If you are familiar with Temple Run, this is sort of like a Temple Run style games, right? So in order to achieve that, there are 3 keywords. Real-time. Real-time means that this type of implicit neural radiance field, they might not be really suitable. And also interactive. In order to do physical-based interaction in real time, we should leverage axillary geometries. But in the meantime, we also need to reason some of the physical properties automatically from this video. For instance, we need to reason what are the units for rigid body collisions. For instance, this car is movable, but this wall is not, right? This is some of the common sense physical knowledge that we need to infer, and so that we could establish a composable scene representation that, consistent of realistic physical behaviors. And in the meantime, we might also need to infer, for instance, the mass or basically the hardness of the object and so on. At this moment, we only want to measure the mass of the physics, and for the friction and other stuff, we'll freeze them in our gaming environment. Now, then, after we build these assets, we can put these assets into a game engine. Here we are using just a very simple 3GS browser-based game engine, but it's coupled with a neural texture mesh, which means its shader is just a tiny little MLP that will give us realistic renderers. So the result is looking something here, right? So given one single video, we're able to build a game. That the game there is a character that is moving around, and also there are some physics. Let's just wait 1 second, and the character can shooting some balls. It's a very simple toyish game demo, and the character can actually hit the vase and putting the vase, making the vase to be interactive with the scene, and so on and so forth. And we could also build another game. This is just a kitty video, a single video. We could actually create a game that character is collecting coins, but in the meantime, it can break down things like the breaking down the chairs and so on and so forth. All right, so that basically wrap up today's discussion. I list a few challenges for existing works in modeling and simulation. Basically, the lack of physical grounding is one of the key issues I do believe in generative AI that we might want to resolve. And we discussed about how to approach that by combining physics and data-driven models. Overall, there are just a few take-home messages. The one is building physics explicitly for visual content creation is usually will help yield more plausible outcomes. And also the quality of view synthesis is definitely not equal to the quality of simulation. And the third one, you might notice that in today's talk, I don't really show a lot of tables with numbers because I don't really trust those type of quantitative evaluation of visual content creation and simulation. There is definitely a need that we might need to come up with a trustworthy quantitative measures, but so far we don't really have a good measure to measure how well we are, except for we inspect those visual qualities. All right, so that's basically all the talk. And in terms of future, I'm really curious about, is that possible that we can rediscover some physical rules from generation? As we can see on the left, we see a very realistic, generated images with realistic lighting. That basically implies the generative AI model actually encodes some of the physical knowledge. But is that possible that we can extract them out and interpret in the way that we could rediscover the physics? So, and also, for instance, in the video generation, we can see quite a realistic, non-rigid, dynamics of the flowers, of the hair, and so on. Overall, both will suggest that potentially there are some optical physics and dynamic physics has been learned. And we can inspect, and then we can correct them. Our generative AI in future is able to encode physics. But so far, it's not really clear how can we achieve that. And also, we should leverage this type of recreation process to be combined with a lot of scientific model to ensure that there is a closed loop to help us to make the decisions in the real world. And this is a power of recreation because it's grounded in the reality. And that's basically summarized my talk. I would like to thank my students and collaborators, as well as the funding agencies. I'm happy to take more questions. Thank you.
We can take a few questions before we have our break.
David?
Hold on.
So this is actually both for you and Greg and Alex and a whole bunch of people in this Nerf game. There is an elephant in this room that everybody's been quiet about, which is long experience with functional representations has demonstrated that it really matters how you regularize them. We've seen a bunch of cases where that is manifesting in Nerf world, but nobody's talking about it. So the floaters that you get with one kind of Nerf, which are the essence of what's causing rendering to be good when simulation is bad. You fill a room with fog, the floaters become obvious.
Yes.
The fact that somehow Greg is regularizing his Nerfs with some sort of unspoken thing, and then there aren't any floaters. There's a trick here that we need to understand, and currently it just isn't understood.
I think it's a choice of what will be the functional representation of the scene. And in practice, what we face is we know some of the functional representation, like our world is explicit geometry, right? We should use that, but it will give us a terribly really hard job to do optimization. So that's why we're leaning towards implicit method. So I cannot find a sweet spot so far, but that will be definitely
But
something.
what is so odd about NERF as a network representation
Yep.
is we have no way currently of regularizing it in contexts of what we know about the 3D world. We can fiddle around with its weights if we really want to, but it's not relevant compared to what we want to control in 3D.
Yes, yes. I don't exactly know the answer, and yeah. Yes.
Thank you so much, Zhang. This was a very interesting talk. So, 2 questions. So, what is the path forward to better simulation then?
Yes, I do think the path forward is we need to, bridge the simulation together with some of the existing scientific model for us to self-correct our simulation loop. Say in the example where I showed that I want to build a simulation of the agriculture, then we could run based on our current observation and based on our scientific model, we could run prediction and predict what's going on in the next 7 days. And then in the next 7 days, we'll have some new observations. And we should allow our simulation to self-correct this, either correct our models or correct our observations, so that we could, in the end, we'll get into a more trustworthy digital twin that could allow us to make informed decisions. So far, this type of simulation is much better at creating visuals than actually helping us to make decisions by giving us a bunch of counterfactual alternatives, and let's try to take one of them based on our simulation output, because our simulation is not really reached the stage to be really trustworthy yet. Yeah, this is one direction I believe is important. Yeah.
And the second question is the physically grounded simulation examples that you showed where you can create data augmentations, right?
Yes.
In my experience, that has like a lot of promise, but then from a very industry point of view, when you go talk to actual people that are building the autonomous recognition systems, right, perception systems,
Yeah.
they always have sort of, concerns about using it because of you could have counterfactual examples in there and things like that. So is there numerical evidence that leads to improvement in accuracy of perception?
Yes, I didn't show here, but in the GeoSim back in two years before, we do showcase that help improve perception itself. It's not yet there to help decision making because we don't really have a very realistic and convincing interactive environment. So that being said, there are more and more evidence. For me, I have seen people train quadruped on simulation and then easily transfer into the real world. This suggests there might be a pathway that we could benefit this type of large-scale simulation environment and more and adapt them into the real world. It just, there is a trade-off, right? We could put a lot of efforts in closing the final reality gap, or we could just leverage the scaling law. We simulate a lot of different cases. That our data cannot really capture. There might be some gap, but potentially because of the fact that the benefit of scaling law actually overcomes those reality gap, we could get some of the benefits. And that being said, I agree with you in some of the situations, like even from a training perception perspective, I don't think the simulation is the final goal. A lot of data augmentation could achieve, some of similar effects. Another important part is actually evaluation, because whenever it becomes safety critical, it becomes terribly hard for us to evaluate. We cannot evaluate self-driving car. There is a baby crossing the street. We will evaluate whether a car will brake or not. There is some information that we should be able to get from simulation. Yeah.
Thank you.
Okay, well, thank you very much.
All right. Thank you.
We will start again at 11 o'clock.